Hey, I'm Piotr, a PhD student at University of Edinburgh. In this video, I will tell you about dynamic memory compression. This work is a collaboration between NVIDIA, University of Edinburgh, and University of Wrocław. This talk will proceed as follows. I'll start with the motivation for KV cache compression. I will discuss the role of KV caching in transformer inference, define what it means for a GPU operation to be compute-bound and memory-bound, and then explain why compressing the KV cache is crucial. Once we understand our motivation, I will describe how our method works during inference and how to retrofit a pre-trained model, such as Llama 2, into a DMC variant. I will then proceed to discuss the results, where I will try to convince you why you should use DMC in your model or application. So, let's start with the basics. Auto-regressive generation with transformer models. One of the primary bottlenecks in efficient LLM inference is KV caching, which involves storing representations of all previous tokens in GPU memory. We do this to avoid the recomputation of past representations, which would be more resource demanding than simply retrieving them from the GPU high bandwidth memory. Now that we understand KV caching, over the next 3 slides, I will explain why it's important to compress this cache. First, let me briefly define what it means for a GPU operation to be compute-bound or memory-bound. This definition is crucial to fully understand the bottlenecks of LLM inference. In general, an operation is memory-bound if the overall runtime is dominated by memory accesses. Otherwise, it is compute-bound. For example, on an NVIDIA H100 GPU, we can perform 200 times more floating point operations per second than memory transfers. This means that if the ratio of operations to memory accesses is significantly less than 200, the operation is likely to be memory-bound. Now, let's discuss memory and compute bounds in the context of text generation with transformers. As we know, in these models, most of the time is spent on computing linear layers and self-attention. Computation of linear layers is memory-bound for small batch sizes because each vector matrix multiplication requires retrieving large weight matrices from GPU memory. However, as the ratio of flops to memory accesses increases with batch size, the linear layers becomes compute-bound. As shown in the plot, the latency of linear layers remain constant up to a batch size of roughly 128. This marks the breaking point, where we transition from being memory-bound to compute-bound. Until this point, additional examples do not significantly increase latency, so to fully utilize your hardware, you should run batch sizes of 128 or more. In contrast, the ratio of floating point operations to memory retrievals for self-attention remains constant and doesn't change with increasing batch size or sequence length. Self-attention is memory-bound, and its latency increases linearly as more tokens are generated. So, one key takeaway for LLM inference efficiency is that we should run batch sizes larger than 128. However, achieving this is challenging. Why? Because of the size of the KV cache. For a relatively small 7B model with a batch size of 32, the KV cache fills up our GPU memory at a sequence length of 4,000 tokens. If we were to process 128 examples in parallel, we would be limited to a sequence length of 1,000 tokens, which is quite short. Addressing this issue of large KV cache can positively impact many important metrics, including hardware utilization, as discussed on previous slides, latency of self-attention, and therefore the entire generation process, maximum number of parallel requests, maximum sequence length one can process, maximum model size one can fit on a single GPU, and used for generation, and so on. Given all of this, I hope I have effectively argued the importance of addressing KV cache size reduction. To achieve KV cache compression, we propose DMC, a dynamic method for compressing key-value tokens. On the left, you see the regular pattern of KV cache expansion for vanilla transformer. At each generation step, a new token is appended to the end of the KV cache. On the right, you see how it works for DMC transformers. Similar to vanilla transformers, but here, you have two options for handling a new token. Either append it to the end of the KV cache or accumulate it with the last token in the cache. Let's go through a simple example. You start with the first token and append it to the KV cache. Then, the model decides whether to accumulate the second token with the first one or append it as a new one. It chooses to accumulate. Again, the third token accumulates. Now, after 3 steps, we have only one token in the KV cache, resulting in a threefold compression ratio. For the next tokens, the decisions are append, accumulate, append. In total, for 6 generations, we have only 3 tokens in the KV cache. To perform DMC inference, you need to predict the decision variable alpha for each token, but you don't need to add any extra parameters to your model. We repurpose the first dimension of the key representation of each token to extract the alpha variable and round it to either 0 or 1, which reflects our decision. DMC accumulation is performed through simple averaging. In the formula shown on the slide, alpha represents the decision to either accumulate or append a given token. Z denotes the running size of the group, which is used to normalize aggregated token representations. The DMC accumulation occurs right after Q, K, and V projections, before the calculations of attention scores. Now that we know how to generate with the DMC model, let's discuss how to train it. Firstly, the DMC decision alpha is discrete. For each token, we either append it to the end of the KV cache or accumulate it with the last token. To train the model to follow this behavior during inference, we need to relax discrete decisions into continuous ones for more informative gradients. To achieve this, we use Gumbel sigmoid as an estimator. On the right, we show example visualization of KV cache evolutions with DMC for both discrete and continuous alphas. Secondly, during DMC inference, each token makes a discrete decision and potentially creates intermediate states that shouldn't be accessible in the future. For example, consider the sequence shown in the middle of this slide. Token K2 decides to accumulate with the previous group, creating a new group of 3 tokens. However, the previous group, represented by K1, will be discarded during inference as it was overwritten by K2. To account for this during training, we modify the attention scores computed within self-attention using a float pooling-aware mask, which is generated based on the predicted alphas. The final ingredient for successful retrofitting of LLMs into more efficient DMC variants is to add compression to the model gradually, in a smooth fashion. GQA, one of the baselines we compare to, compresses the KV cache by sharing key value heads across query heads. To achieve this, they take a pre-trained checkpoint and pull a group of KV heads into one shareable head. During our experiments, we observed that such abrupt change heavily degrades model quality, and it is much more sample efficient to convert the model gradually. For DMC, we start the training with no compression at all and linearly increase it to the target value with an extra objective in an end-to-end fashion. As shown on the right, DMC is able to retain original model performance for both 2x and 4x KV compression, while GQA fails to recover it even with over three times more training steps. Let me now discuss the results of DMC. We performed throughput benchmarks across 3 model scales, 7B, 13B, and 70B parameters. Our implementation is based on the state-of-the-art library for training LLMs, Megatron LM from NVIDIA. We developed an efficient DMC GPU kernel and used paged attention and flash attention libraries. We measured throughput on an H100 GPU for sequence lengths of 4000 tokens. As shown on the right, the DMC compression ratio translates almost perfectly into throughput improvements with up to 7x increase in throughput for 8 times compression. We evaluated DMC models on a large set of commonly used academic benchmarks. Additionally, we compared DMC performance against the commonly used GQA method and state-of-the-art KV eviction policies, H2O and TOVA. Generally, DMC outperforms other compression methods across all scales and compression ratios. DMC LLMs retain vanilla performance up to 4x compression and fall behind by only 2% on the MMLU benchmark for 8 times compression. Moreover, we evaluated whether DMC can be combined with GQA to yield compound gains. Unlike the smaller models from the Llama 2 family, the 70B model was trained with GQA, which compresses the KV cache by 8 times. We applied an additional 2 times DMC compression to achieve a total compression of 16x. Contrary to other KV eviction policies, we fully retained the original model performance with 16 times compression across all benchmarks we tested. As I mentioned earlier, DMC transformers are trained to gradually increase their compression ratio throughout the retrofitting process. This strategy allows the model to decide where it wants to compress, specifically in which layer and in which head. You can observe how the compression evolved during training, starting with no compression and reaching 4 times compression at the end. In general, we observed that DMC LLMs prefer to compress in higher layers, which is consistent with prior work. We believe this occurs because token representations in higher layers are more refined, allowing for better and stronger compression. In conclusion, we propose dynamic memory compression, DMC, a novel KV cache compression method which is applicable to state-of-the-art large language models through an inexpensive continuous pre-training. It adds no new parameters to the model. It achieves 4 times KV compression without degradation and 8 times KV compression with minimal performance degradation. It's simple to implement with existing inference techniques such as flash attention or paged attention. Finally, it composes well with GQA, providing promising opportunities for future research in this direction. Thank you for listening.